everyone. We have finished a lot on beams. We have understood beams in details for the stresses in bending and stresses in shear, and also we have understood bending strain, right? So bending stress follows bending stress. So if and we have seen that few points that came up is for a homogeneous linear isotropic beam, a few assumptions are made for the analysis of the beam. The assumptions are: number one, the beam is in pure bending. Number two, plane sections remain plane before and after bending, right? Or lines normal to the neutral axis remain normal before and after bending. So they remain straight and normal, right? They don't twist. Fourth, we understood a few more details on the beam. Example, neutral axis does not have any elongation. Its length neither changes, neither contracts nor expands before and after bending. So it remains same before and after bending. For a sagging type of loading, the beam will have compression to the top and tensile towards the bottom of the neutral axis or towards below the neutral axis. Right? For a hogging type of moment, the things will be completely opposite. Hogging is a pure cantilever case when you have a top load on the cantilever down on acting. In that case, the tension will be in the top and compressions will be at the bottom of the neutral axis. Okay. We also understood that neutral axis is a geometrical parameter for a beam which is linear, isotropic, and homogeneous. Right. Even we calculated second moment of area, which is also a geometric property for beams. Then we did solve a few problems. We understood a little bit more details on the beam. The bending stress is a normal stress. It's not a new thing. It's the same normal stress acting along the direction of the x direction, or the longitudinal axis direction of the beam, right? But there is no axial or longitudinal force acting on the beam. This stress is generated due to the moment or bending moment at a cross section, right? So we have seen that the top-sided compression, it gives a compressive force in overall equivalent compressive force, and the bottom of the neutral axis provides a equivalent tensile force. So these two are equal and they provide a couple, and that couple is equal to bending moment at that cross section, right? So these are the few things that we have understood from our discussions in the previous classes. And we also seen that bending stress vary linearly from neutral axis toward the top, right, or toward the bottom. And the maximum is given at the top and the bottom fibers. So maximum tensile for a sagging moment will be at the bottom fiber, and maximum compression for a sagging moment will be at the top fiber. And we've defined a formula for finding stress. Sigma x is equal to, or we write it sigma b also because it's bending stress. So sigma b is equal to my by I with a negative sign in the front, right? The negative sign comes because when y is positive, that means towards the upper side of the neutral axis, you have a compressive stress, right? So towards the upper side of the neutral axis with a positive y, you have a compressive stress, therefore there is a negative sign that's going to come. So my by I. So y is the distance from the neutral axis, and therefore it varies linearly with respect to neutral axis, from the neutral axis. Whereas for shear stress, it is different. For shear stress, it varies with the square of y, and not it doesn't vary from, it's not, it varies such that it's maximum at the neutral axis and zero in the top and the bottom fibers. Okay, quite contrary to the bending stress, and therefore it follows a second order parabola format, and we have understood how to draw them. But all these that we said, all these that I have said are for beams which are isotropic, linear, and homogeneous. Now, many of these will be correct for beams that are not homogeneous also. So let's see. So today's class is to look into composite sections, and we discussed, when deriving the moment curvature relationship, that E is a constant for homogeneous isotropic material, right? Homogeneous isotropic beam. But for a composite section, when I say composite, it is not a homogeneous section. It will be homogeneous for certain parts, and then there will be another material that will come into the picture, and therefore E as a constant is not uh, true for a composite section. Now, before we jump into the analysis of composite sections, let's look at why we need composite section. Can anybody answer me why do we need composite sections in the chat?
Sir, there are
Yeah, tell me.
Sir, while bending, what happens is in the top, what if there is a different normal stressor than in the bottom? Like if we have neutral axis not along the geometric center, and in the top there is a different maximum stress, and in the bottom there's a different maximum stress. So to like have different if you have different materials, we'll be able to tackle that.
Very nice. Yes. Anybody else has to add on this? No one? So, as Archie said, for designing cost effective, what happened? I forgot the spelling of cost. Cost effective. And then efficient. When I say efficient, it's not only because of cost, it's because of energy can be efficient. It's because of space, or mass, right? So efficient products or structures. Or even when I say this, what I mean is, let's take an example. Let's say I have, do I have a wing here? No. Let's say I have a aircraft wing. Okay. This is called airfoil, and it's going like this. Okay. So this is chord and that's called span. Now, if I look at the aircraft wing of a plane or something, it basically bends along the chord line, right? It can go like this, or it can go like this, or it can stay straight. But it is not wise idea to bend it along the span direction. It does bend because it's a cantilever beam. So therefore, if there is any aerodynamic load at the tip, it will definitely bend. Cantilever beams cannot hold that strongly, right? So it will definitely bend. But you will expect that bending is very small, because that bending is going to create vortices, and that will actually react with the aerodynamics of the whole structure, right? So you would like to keep it as small as possible, whereas you would like to keep this part, chord along the chord, maybe more and more flexible, such that you can bend them easily. You can bend them like this, or you can bend them like this, or you can keep it straight while it is in light, cruise condition. So for efficient fuel consumption, you need to do that, but along the chord direction, not along the span direction. Okay. So therefore, you need a material which is flexible along one direction, but not flexible on the other direction. How are you going to do that? Any material you take, aluminum or steel or wood even, right? Whatever you take, will have E, since it's a homogeneous isotropic material, it will have E same along all direction, right? So we probably cannot use them directly. Therefore, if you use composite, if I use composite and if I weave the material such that it is flexible along one direction, so this is my flexible material, and this is a little bit stiffer material. I weave them like this, and I get a new material. Then I can satisfy both my requirements, that it has to be stronger span direction and flexible in the chord direction. Okay. There, I need to make two materials and weave them, right? This weaving of two materials is called a composite sections or composite beams. If it's a beam, it's called composite material or composite structure. And this is heavily used in industry nowadays. I think industry cannot work with composites in another few years. It will be, even engine blades are made composite nowadays. They don't make completely full thing, but one or two of them are made composite. Slowly, probably they will go to full composite engine, right? And other requirements are also very well satisfied. Lightweight. These are very light weight. Therefore, strength to mass ratio is high, right? One of the problem, is if we want to have higher strength, we put more material mass, right? For example, cars, old cars, if you see, they are made up of complete metals, right? And they're very heavy. Now, when they're heavy, they might be more robust, but they cannot run fast because it has to carry its own weight, right? You're adding weight. Therefore, light cars have come. Now, light cars have their own, problems. They can topple easily, that because they are not very robust or stable, but they can be very fast. World has become fast now. Therefore, you need some materials which has high strength to mass ratio. That means you can add more strength without increasing mass heavily. Right? Because cars can go and collide, so it needs to have accidents happen, so it needs to have more strength. But you cannot add on mass, because if you add on mass, the speed you have to compromise, which you don't want, because all your customer will look into the speed. So you need to design for composite sections, because composite sections are lightweight and they give you higher strength in whatever direction you want. So if you want a directional strength, composite materials are the best to go. Okay. These are the few reasons. There are many more. There are the few reasons for which we make most of the designs and composite sections. Plus, they're easy to make in the sense that if you have a mold, if you have a furnace to make a composite section, you can easily do it. Whereas for metals, it's not only the mold that is important. For example, uh, let's say a cone of a rocket. Okay, cone of a rocket looks like this, the top portion. Now, it's not difficult to do it with metals, but it's much easier to do it with composites because you just need a mold to do that. Okay. But there are, once you change from metal to composite, there are also issues with composites, right? Some of them are really very critical issues are not solved even in last 20 years. One of them is debonding. So when you add two materials or weave two materials, okay, you attach them with respect to a glue. We call it matrix. So with a matrix or a glue. Now what happens that glue, in its very, when it is new, it is very flexible. But as it grows older, it becomes stiff and stiff, and therefore it doesn't show any ductility. It becomes brittle and break. So when the glue breaks between two layers of material, what happens is you start getting debonding between the two materials. And where there is a debonding, the load will not transfer from one material to the other material. And if it doesn't transfer, it will start breaking from there. Okay. Next is, if you have a composite and it has somehow failed, composite repair is not an easy job. Okay. Why I say this? Because our industry is not yet up to the mark for composite repairs. So metal repairs are going on for hundreds and hundreds of years. So we have come to a stage where quite mature with metal repairs, right? Anything, in metallic that breaks, for example, car, metallic, it breaks. You go, they do some hammering, they put a plate, they will do a lot of things, they do welding, it will be working, right? But composites, You cannot do welding. You have to replace the complete part. Okay, so the repair part or the maintenance cost for composites are quite high. Okay, plus we don't have sufficient trained manpower to do that. So composite repair is still part of research. Another example just came to my mind is body armor. For army, we have body armors, right? So that bullet cannot penetrate and kill the person or damage the personnel. Earlier days, if you see, might have seen it in movies. You might have seen it in history channels, documentaries, and other things. That earlier army, cavalry or whatever you have, they used to wear a heavy, thick, metallic vests, right? Now these metallic vests are quite heavy. So when you go for war, when you carry them, it's not very comfortable, neither very easy to carry them long time, right? So you get fatigue very easily. Whereas if you have a light but strong, like a composite thing, you won't feel it. It's like a backpack you are carrying, right? So it reduces, the fatigue that army or the personals feel. So that's another example where it is heavily used to make body armors. Okay, and in that case, they need to work, right? You cannot say that there can be debonding and it's okay. No, they need to work. They need to dissipate energy. Okay, so these are the few things that makes composite very attractive, but still there are a lot of research that can be done in composites, and probably one of you can take up because it's heavily used in industry. It's going to be heavily used in industry in next couple of decades, and there are a lot of what should I say, a lot of opening in this area. Not only in composites of polymer materials or normal material, there is composite metal matrix composite can also be there, right? So you take it up. In this course, we learn not even 1% of composite things. We learn, but we understand how composite materials work or composite sections work as a beam, how to analyze. So the method that we are going to understand, not today's class, in the next class, is going to be useful for you all through, right? Because that's the basic, that's the standard that is used. Our various version of that is used for different kind of composites, but it's the same thing that you have to do in all the methods that you use. Okay, it's called equivalence. So you find equivalence between different materials that you have, and once you find that equivalence, you convert them all to a single material and then analyze. That's what you are going to do in any method that you use for composites. Even for even for building materials that we have around, they are all composites because they are made up of cement, concrete, and then metal. That means steel rebars, right? So they are composites. So steel rebars are used for taking the tensile load, whereas concrete is used to take the compressive load, right? But they are cost effective. Otherwise, I would have made a building made up of completely steel, right? But we don't do it. We don't make buildings of complete steel because they won't look good. They are very costly. We make bridges completely of steel, right? Steel bridges are available, but not steel buildings. Buildings are made by by normal people, right? So normal people cannot pay that high amount for a steel. But when you make a bridge that has to sustain for 50, 100, and 150 years, you need to make it very, very strong, and government can pay for that because it's an investment for 150 years. But when you make a building, you don't generally look into 150 years. You look into your lifetime and maybe a little bit of your next generation, right? So your design for building is maybe 50 years maximum you look into, but buildings can survive 150 years. That's there are a lot of buildings which survive 150 years, but your lookout is not 150 years. But when you make a bridge, your lookout is of that range. Therefore you make it made up of steel. But we don't make buildings of steel, we make it of concrete and steel, a composite. Okay, I've said a lot. I think you might get bored now. So here are a few things of composite. So research in composite design, composite manufacturing, composite testing, composite failures and repairs. These are the various areas where you can go ahead and do research. Your BTPs also. We have few faculties doing composites in our department. I think Professor Arukya Rajan works in composites heavily. I work in composites as an application area, and we have got a few projects on composites from defense. Yes, so I look into dynamics of it, and he looks into static part of it. Dynamics of composite sections, yes, that has not yet picked up heavily, and that's a tremendous area of research because unlike your homogeneous materials, composite sections undergo nonlinearity very easily. They can go large deformation. I can design them for large deformation. They can go bistability, within their linear zone itself, not linear zone, within the linear elastic part itself. Okay, so we have a lot of scope for dynamical analysis on composite sections. Okay, right. So this is what we do in our course. We'll do. So we'll take mostly two composite sections. One will be made up of one material with E as its Young's modulus, and the other will be made up of another material with E2 as its Young's modulus. Composite pipes can be there. This is wood and metal composite, which is used to be heavily used in civil structures and probably to make foundations of machines. There is a woven. This is an example of a woven composite where you get E1 and E2 properties at different directions. Okay, so that's one thing. Here you see this is how it happens when you have a debonding. So these are the materials along this direction, these fibers, and these fibers are along this direction. Okay? So they have strength on both the directions. But if it happens debonding, they cannot transfer load from one side to another. Okay, these are a few examples. You can look into more examples. This is another woven fabric. This what we can make in our labs easily. I think you have not done it, but it was part of your workshop. If you come and do a workshop, you have to probably make one of these in our workshops. Okay, now the first part of the composite analysis. What are the assumptions that we're going to make? We stick to the assumptions that we had during bending, for homogeneous materials. One, cross sections remain plane before, during, and after bending, and pure bending conditions are considered. Okay. Linear elastic material, so we don't go to nonlinear zone of it. Bonding between the material is perfect, and we neglect the effect of bonding material. Okay, so we assume there is a glue between this layer of two metals or two materials, and that glue is there, but we don't consider it to be there, and we assume that the glue is perfect. That means there is nothing, there is no shear relaxations at those points. There is no whatsoever. There is no effect of the glue. The glue doesn't contribute to the strength, neither it affects. So we are assuming that glue is almost negligible. Next part, the longitudinal strain. This is very important. Epsilon x in a composite beam vary linearly from top to bottom of the beam. When I say linearly, I mean along the joining location, this location where it is joined, the strain, longitudinal strain or the bending strain is what's the continuous. It's not discontinuous. Okay. Right. Why is that? Because I'm assuming both the material is perfectly bonded, and therefore at this junction where the two materials are joining, right, there won't be any difference in their deformations. So whatever metal one goes, whatever deformation metal one will have, same deformation material two will have at this location, at this joining. Otherwise, one will, let's say one goes more than the other. If one goes more than the other, then the bonding is not perfect, right? Therefore, we are assuming that at this location, both of them have same deformation, and therefore they at this location both of them will have same strain. So strain goes like this. As you can see, this is strain. So strain is continuous here. Okay. The reason I have already said. But now, from strain to stress, if I have to go at this location, a little bit above that, I have to multiply with E1 to get stress, and a little bit below that, I have multiplied with E2 to get its stress, right? So the strain, although equal at these two locations, the stresses are going to be different because they're going to multiply with two different E. And therefore, at this junction, there will be a discontinuity in stress. There will be a jump in stress. And this is the jump. This jump is due to E1 by E2 or E2 by E1. Okay. So as I said, this one sigma A, sigma 1c is going to be E1 into epsilon A. C, and this is going to be E2 into epsilon C. Both have same epsilon, but they have different E, and therefore there will be a jump. So always remember the point where the location or the point where two different material sections are joining, you will have a jump in stress, but not in strain. Don't forget this, not in strain. And that comes from the geometric constant that we have. The geometric constant is I cannot allow one material to deform more and the other material to deform less at that junction where they are connected. It's called compatibility condition. And that compatibility conditions will allow me to make the strain to be continuous, but stress has to jump. Okay, clear? Very nice. Okay, now let's look into the curvature relationship, moment curvature relationship between the composite sections, right? For a single material, homogeneous material, we understand that the relationship that is to find neutral axis, okay? It was sigma x into dA equal to 0, where we converted sigma x equal to minus epsilon kappa y into dA. And then we say that E is constant for a single material, and it goes to 0, right? E is constant for a single material, single homogeneous material. Okay, so you get into y dA to be equal to 0, and you find neutral axis. So neutral axis becomes actually not a material property, but a geometric property. It's a y dA, right? There is no material here. It's a y dA for a homogeneous material. But for non-homogeneous material, what happens? You have two E's, right? Right? And therefore you cannot do that. This tape is not allowed in a composite section. So what we do? Let's take two composite sections we have, right? Not more than two. In our syllabus we have only two. So this is E1 and this is E2. E1 and E2, right? So now we again there is no force that is acting along the longitudinal direction, and therefore our total force along longitudinal direction is going to be 0. And therefore this relationship sigma x1 dA plus sigma x2 dA. So before that I will write this equation itself. Should be equal to 0. Now that is made up of two materials, right? The cross section is made up of two materials. So I can write it one material into this plus two material into this. Sorry, integral of this equal to 0, right? So one of them has sigma x1 as its stress and one of them has sigma x2 as its stresses. Some of the forces about the neutral axis are going to be 0 because there is no horizontal force acting on the material. Now I can replace them with their normal relationship that we have between stress and the curvature, epsilon E1 kappa y, E2 kappa y. Remember that for curvature stress relationship, we need only one assumption, that is normal sections remain normal above the neutral axis before and after bending. That we have considering for composite section also. So this is valid. From this to this is valid. Now, since E1 and E2 are different, right, I cannot put them to 0. what I can write is full equation like this to be equal to 0. And this relationship is going to give you neutral axis. This is one single equation, and neutral axis location will be only one unknown. So you can find neutral axis from this. Okay, so I've written plane sections remain plane is the relationship that you need to come from this to this. Now use this relationship to find neutral axis. Now you see we cannot put U1 and U2 to be 0, they are there. Let's see how to find neutral axis for a section like this. So this is a composite section which is made up of wood on the top and steel at the bottom. Okay, all right. We need to find its neutral axis. So since they have different E, the neutral axis is not going to go through the center of the cross section, right? It's not homogeneous material. Okay, so we assume that neutral axis is to be H1 location from the top. So it's at this point we assume the H1 location from the top is the neutral axis. We need to find the value of H1, right? And we know that steel wood is of larger area or larger length, right? Larger depth, so it has to go from the wood. It cannot go through the steel. It can if you want to make it so that it goes. If the steel becomes a little bit thicker, probably it will go through the steel. So now what we do is we have to use this relationship, right? So first we find for the material 1 what is integral of y dA. It's going to be y1 bar into A1, right? So A of the steel, A of wood into y1 bar, right? Y1 bar is its neutral axis of the wooden section from your assumed neutral axis, right? So H1 minus 3 inches, so this is 6. Central line of wood is going through the 3 portion. So from here, if I look at, this is my H1 and this is my 3. So the difference is this much, right? So H1 minus 3 inches, and then the area is going to be 6 into 4. This is the area, right? Hmm? And if you do the calculation, you get something like this in terms of H1, because we don't know H1 yet. Next is Y2. We have to find Y2, A2. So this is my Y2. This is my A2. Please note the sign negative here, minus. So we are now calculating from here. This is 6.25. The central line of the steel member going through is 6.25 from the top. And then we are subtracting H1. So this is the distance between the center line of steel with the neutral axis, assumed neutral axis, and it is on the bottom side, right? So negative of y, therefore there is a minus sign. Okay, so now you do that, you get something like this. Here also in terms of H1. Now you put them back here into the expression for neutral axis that you have. Once you put it back here, you have E1, E2. These are E1, E2. You do all the calculation, you finally find H1 to be 5.031. So from here, it is 5.031. So something here is your neutral axis. Please note, neutral axis will shift towards a heavier E. Heavier in the sense who has higher E. Okay. If your E2 is higher, it will shift towards E2. If your E1 is higher, it will shift towards E1. So wherever the material is higher, it will shift towards that, because that will weigh your those new portion more, because these are like weighing factors, right? For this material, can you tell me where will be the neutral axis? So it is a section, composite section, where there is a steel on the top and steel on the bottom, and both have same thickness T, and in between there is wood. Okay, of height something H minus 2T. Now look at the symmetry. This is a symmetric section, right? Because top and bottom has same thing. It has to go through the center of the cross section. Now do it yourself, do the calculation yourself, and find out whether really it goes from H by 2 or not. Put some values and find it out. Even if you don't need to put value, it will come out with these variables itself. Now look at moment curvature relationship. That is another thing that we have to find out. Very simple. Moment is, we know, minus of the normal stress that we have. So this is going to be the moment. Now this sigma xy is not a single, is due to two materials, so you can just extend it for two materials. And once you extend it for two materials, you can relate them with E1 and E2. So it becomes kappa E1 y squared dA and kappa E2 y squared dA. Similar formulation like previous homogeneous material that we did. Now this is I1 and that is I2 because this is about the area 1 and this is about the area 2, right? And then you have to convert them to the neutral axis. So you have to use, you know, that formula AD square, right? You have to shift moment of area from one axis to another axis. Now, if you write them as kappa E1 I1, kappa E2 I2. So kappa E1 I1 plus kappa is constant, so goes away. Kappa is a geometric property, not a material property. This shows even for composite section, kappa is a geometric property, not a material property. E1 I1 plus E2 I2. So kappa is going to be 1 by rho m by E1 I1 2 I2. Okay, once that is done, you can find sigma x1 is m y E1 by E1 I1 plus E2 I2. Similarly, here also m y E2 by E1 I1 E2 I2. Now, if you look at this, do you remember where have you seen this? You have seen it in both axial as well as torsional member formulation. When you have multiple materials, right? Different materials, and then you have to divide. As I said that the by which the stresses are going to be shared depends on their relative rigidity with respect to the total rigidity. So this is the rigidity of a beam. EI is called rigidity of a beam, or we call it bending rigidity. Okay, so you remember that we had A1 E1 plus A2 E2 A2 so on and so forth, and on the top we had E1, right? Something like that. PL by AE deformation when we found, we had some relationship like that, right? So this is the total rigidity of the section. This denominator is the total rigidity of the section, and in the top you have this material part properties. Okay? So please remember this. I'll say it again that the stresses or the deformations are shared based on how the relative stiffnesses or rigidities work with respect to the complete rigidity at the joint. Let's look at it. There is this composite section which we just solved to find neutral axis. So this composite section is made up of wood in the top and steel in the bottom. Remember that this kind of section you can use for sagging kind of bending, not for hogging. Okay, because sagging, it is more tension at the bottom. The last fibers will have more tension, and metal is good for taking tensions, whereas wood is not good for taking tension. It can take tension, but not as much as metals. Okay, so that's why you use this kind of section only for sagging moments. For hogging, you have to use something like this. All right, because in that case, moment and tension will be at the top. Okay, so this is the composite section. A composite section looks like this. This is not a beam. This is a section of the beam, and the properties are given. Its wooden part is 6 inches and its metal part is 0.5 inches. Okay, and the width is given as 4 inches here. E1 and E2 for different material is given 1500 and 30,000 ksi on per square inch, right? And we need to calculate the largest tensile and compressive stresses in the wood and in the metal, right? That is what we have to find out. Okay, first thing is number one work is to find neutral axis. We have found it. It is h equal to 5.031 inch. So from here, it is 5.031 inch. And so h2 will be some 6.5 minus. You can find it out. One more thing you have to do is take a ratio of E1 by E2, and this will be useful later. Next job is to find neutral axis, second moment of area, right? Not inertia. These are moment of area. All that same thing. Instead of mass, you have area. So second moment of area you want to find. Then what do? You have to use parallel axis theorem because neutral axes are not passing through the neutral axis of either of them. Therefore, you have this half 1 by 12 BD cube for I1. I1 is here and I2 is here. And then you have to shift it, right? Shift the neutral axis. So H minus 3 inch. You will get something. I2 also you will get something. I'm asking you again that if you do not, if you have not practiced, please practice how to calculate moment of area, second moment of area. Also, if you don't understand second moment of area, how to find them, please get back to me. I'll record a small video and send you. Okay, right. Please also note moment of area acts as a tensor. So you can transfer them, you can rotate them, but you have to use tensorial rotation formulation for that. So if you don't know those things, please get back to me or read a proper chapter or proper book where you can find principal directions for this, moment of areas. There will be one will be maximum principal direction, one will be minimum principal direction. The bending of always the failure will be along the minimum principal direction, the bending about the minimum principal direction. Okay, right. Now we need to find the next job is to find normal stresses, right? Now to find normal stress, we need to find where are we going to find normal stress. Of course, one of them is the top point because that will be the maximum. The bottom point because that will also be maximum. But again, probably we need to find my normal stress at point C at the two materials. Okay, because there will be jump there, right? And your glue has to take up that jump stress. So where is this jump? How much is the jump? You have to find out. So this is the four places you might need to find. Apart from that, if there is something else in anywhere, it is asked you have to find the normal stresses. Now normal stress in the first material will be given by this formula. We just derived it. And in the top fiber, where your y is going to be h1. And if you calculate that, you get this. Compressive. Sigma 2b at b, that means at the bottom here, it is going to be minus h2 because from neutral axis, this is h2 here. And that's h1. So from neutral axis, it is h2. And you have to use the values for E2 here. Here you have used E1, here you have to use E2. And you get something. You can see the highest, the value. It's almost like 5 times of this. Right? More than 5 times, maybe 6 times. It's 13, 78, yeah. Almost like 6 times. Right? Because of the metal. Just because of the metal, it can carry so much of load. Had it been completely steel, completely wood, then it would have made only 1300 to 1400 maximum, right? At this load. But now since I put steel here, metal, I get lot of tensile stress to be taken care by the section, right? But if I made complete full section of steel, I might get similar kind of stress carrying capacity or load carrying capacity for the members. But I may not need it in compression. Maybe the section doesn't take the need that much of compressive resistance. In that case, this will reduce the cost, more efficient design. Now at location C in material 1, it will be same thing, M1 into whatever this distance is. You have to calculate and put that here. And 1500 is for E1, at E1. And this is at 2. Okay, so this is E1. This is E2. And you see the jump here. 251, in the same location in material 1, it is 251. Whereas in material 2, it is 5030. And if you take the ratio of these two, it comes out to be 20, which is E2 by E1. This ratio is always equal to ratio of E2 by E1, the jump. Okay, now we have to draw it. So for strain, we know it's going to be linear. There is not going to be any change. So strain is like this. There is no jump at the location where your metal and the wood is connected. But in stress, you know that this stress is 251, whereas this full stress is 5030. So there is a jump here. Okay, and then again linearly going down to 707,620. And here also like this. Okay, so there is a stress jump and you have to calculate the jump. Any questions that you have? With that, I'll stop. Any question that you have?
Sir, um, no, sir.
Yeah, carry on.
Small, like, sir, here actually asks us to find the maximum stress now, sir. Like, yeah, right, sir.
Yes, yes.
So maximum stress we need to find means like anyhow, like it's going to be maximum at the corner. So why do we need to find a jump, sir? Because like jump is anyhow like it's going to be lesser than the stress at the end, sir.
Very right, Karikeswar. But when a design problem is given to you, you have to do this. You have to show all these things. It's no more. And I don't know whether your questions, your exams will be online again or not. But if you do it in pen and paper, it is always a good idea to show all the critical points, what are the stresses, if you have time, and draw the stress diagrams. Okay. Please note, I will not ask you. The book has asked you to find the maximum stress, calculate the largest tensile stress and compressive stress in the wood material, and the maximum minimum tensile stress of the steel material. Right? Book has asked, but whenever I'll give you a problem, I'll ask you for all the points, all the critical points. And it is a good idea to always draw whatever stresses comes at all the critical points of the beam.